And we are back to use the DOE Volume 3 book to talk about fluid flow. So if you look at the three different volumes, the first volume is the volume that covers thermodynamics. The second volume, so there are three volumes for this class, covers heat transfer. And we talked about conduction, convection, and radiant heat transfer. And so now we're into this third volume where we're talking about fluid flow. And fluid physics, I think, is quite interesting because of it describes the relationship between the different types of energy in fluid stream through the use of Bernoulli's equation. And so in this module, we're going to discuss the causes of head loss in fluid systems and what factors affect head loss. Okay. So for this module, this volume 3 is thermodynamics, heat transfer. Now for volume 3, we've gotten into fluid flow. And like I said, fluid physics is quite interesting. So the overall objective is given conditions affecting the fluid flow in a system, evaluate the effects on the operation of the system. The enabling objectives for this third volume is to describe how density of a fluid varies with temperature, define the term buoyancy, describe the relationship between pressure in a fluid column and the density and depth of the fluid to state Pascal's law. Define the terms mass flow rate and then volumetric flow rate. Calculate either the mass flow rate or the volumetric flow rate for a fluid system. State the principle of conservation of mass. Calculate the fluid velocity or flow rate in a specified fluid system using the continuity equation, and describe the characteristics of flow velocity profiles in laminar flow and turbulent flow. Also define the property of viscosity and describe how that viscosity of a fluid varies with temperature, and describe the characteristics of what we call an ideal fluid. Describe the relationship between the Reynolds number and the degree of turbulence of flow, and describe the relationship between Bernoulli's equation and the first law of thermodynamics. Define the term head with respect to fluid flow. Explain energy conversions that take place in a fluid system between velocity, elevation, and pressure heads as flow continues through a piping system. Given initial and final conditions of a system, calculate the unknown fluid properties using the simplified Bernoulli equation. Describe the restrictions applied to Bernoulli's equation when presented in its simplest form. Explain how to extend Bernoulli equation to more general application, and then relate Bernoulli's principle to the operation of a Venturi. Just define the term head loss, frictional loss, and minor losses. Determine friction factors for various flow systems using the Moody chart. Calculate head loss in a fluid system due to frictional losses using Darcy's equation. Calculate the equivalent length of pipe that would cause some head loss as the minor losses that occur in individual components. Define the natural circulation and forced circulation. Define thermal driving head. describe conditions necessary for natural circulation to exist, explain the relationship between flow rate and temperature difference in a natural circulation flow, describe how the operator can determine whether natural circulation exists in the reactor coolant system and other heat removal systems, and describe how to enhance natural circulation flow, define two-phase flow, describe two-phase flow, including such phenomena as bubbly, slug, and annular flow. Describe the problems associated with core flow oscillations and flow instability. Describe the conditions that could lead to core oscillation and instability. Describe the phenomenon of pipe whip, the phenomenon of water hammer. Define the terms net positive suction head and cavitation, and calculate the new volumetric flow rate, head or power for a variable speed centrifugal pump using pump laws, and describe the effect of system flow and pump head for the following changes. So changing pump speeds, adding pumps in parallel and in series. So the first chapter, we're going to talk about the continuity equation. So understanding quantities measured by the volumetric flow rate and mass flow rate is crucial to understanding fluid flow topics. The continuity equation expresses the relationship between mass flow rate at different points in a fluid system under steady state flow conditions. And so the enabling objectives for this particular chapter is to describe how density of a fluid varies with temperature, define buoyancy, and describe the relationship between pressure in a fluid column and density and depth of the fluid, to state Pascal's law, define the terms mass flow rate and volumetric flow rate, and then calculate either the mass flow rate or the volumetric flow rate in a fluid system. So fluid flow is an important part of most industrial processes, especially involving the transfer of heat. So frequently, when it's desired to remove heat from the point at which it is generated, some type of fluid is involved in the heat transfer process. Examples of this are cooling water circulated through a gasoline or a diesel engine, airflow past the windings of a motor, and then the flow of water through the core of a nuclear reactor. So fluid flow systems are usually, are common way to provide lubrication. So fluid flow in the nuclear field can be complex, and it's not always subject to rigorous mathematical analysis. Unlike solids, the particles of fluids move through piping and components at different velocities and are often subjected to different accelerations. So even though a detailed analysis of fluid flow can be extremely difficult, the basic concepts involved in fluid flow problems are fairly straightforward. These basic concepts can be applied in solving fluid flow problems through the use of simplifying assumptions and average values where appropriate. So even though this type of analysis would be sufficient in the engineering design of systems, It is very useful to understanding the operation of systems and predicting the approximate response of fluid systems to changes in operating parameters. So the basic principles of fluid flow include three concepts. The first, which is the student, which the student has been previously exposed to, is momentum, leading to the equation of fluid forces, which is covered in a manual on classical physics. And then the second is conservation of energy, and that leads to the understanding of the first law for thermodynamics. And then the third is conservation of mass, which leads to the continuity equation, which is explained in this volume 3. Okay. So momentum, conservation of energy, and then conservation of mass. So properties of fluids. A fluid is any substance that flows because its particles are not rigidly attached to one another. This includes liquids, this includes gases, and even some materials that are normally considered to be solids, such as glass. So essentially, fluids are materials in which they don't have a repeating crystalline structure. Okay. Several properties of fluids which are discussed in the thermodynamic section of the text, and these are temperature, pressure, mass, and specific volume. Remember, we said that these are extrinsic properties. Temperature was defined as the relative measure of how hot or cold a material is. It can be used to predict the direction in which the heat is transferred. Pressure was defined as force per unit area. Common units for pressure were pound force per square inch, or PSI. Mass was defined as the quantity of matter contained in a body, and it's distinguished from weight, which is measured by the pull of gravity. Specific volume of a substance is the volume per unit mass of the substance. And the typical units are cubic feet per pound per mass. Density, on the other hand, is the mass of the substance per unit volume. And the units were pound per mass per cubic foot. Density and specific volume were the inverse of one another. And density and specific volume are dependent on the temperature and somewhat on the pressure of the fluid. So as the temperature of the fluid increases, the density decreases and the specific volume increases. So since liquids are considered incompressible, an increase in pressure will result in no change in density or specific volume of the liquid. In actuality, liquids can be slightly compressed at high pressures, resulting in a slight increase in density and a slight decrease in the specific volume. So buoyancy is defined as the tendency of a body to float or rise when submerged in a fluid. And so we have all had numerous opportunities to observe the buoyant effects of a liquid. So when we go swimming, our bodies are held up almost entirely by water. Wood, ice, and cork float on water. And when we lift a rock from a stream bed, and it suddenly seems heavier when we lift it. So boats rely on buoyant force to stay afloat. And the amount of buoyant effect was first computed and stated by Archimedes. When a body is placed in fluid, it is buoyed up by a force equal to the weight of the water that was displaced. So if a body weighs more than the fluid that's displaced, it sinks, but will appear to lose an amount of weight equal to that of the displaced liquid, as our rock. So if a body weighs less than So if a body weighs more than the liquid it displaces, it sinks, but will appear to lose the weight equal to that of the displaced liquid. If a body weighs less than that of the displaced liquid, the body rises to the surface and eventually floating at such a depth that it will displace the volume of liquid whose weight will just equal its own weight. So a floating body displaces its own weight of liquid in which it floats. Compressibility is the measure of the change of volume a substance undergoes when a pressure is exerted on the substance. Liquids are generally considered to be incompressible. For instance, a pressure of 16,400 psi will cause the given volume of water to decrease by 5% from its volume at atmospheric pressure. Gases, on the other hand, are very compressible. And so the volume of the gas can be readily changed by exerting an external pressure on the gas. So the relationship between depth and pressure, anyone who dives under the surface of water notices that the pressure on the eardrums at a depth of even a few feet is noticeably greater than when they're at atmospheric pressure. So careful measurements show that the pressure of the liquid is directly proportional to the depth, and for a given depth, liquid exerts the same pressure in all directions. So as shown in figure 1, the pressure, as shown in figure 1, the pressure at different levels in the tank varies, and this causes the fluid to leave the tank at varying velocities. So pressure was defined as force per unit area. And in the case of the tank, the force is due to the weight of the water above the point where the pressure is being determined. So here they have the equation: pressure is equal to force per unit area, or that force you can substitute in weight. So force is equal to mass times acceleration, but in this case, we're talking about acceleration due to gravity, and force is equal to mass times g, or m times g, which is acceleration due to gravity, and then they substitute in weight, okay? So weight is also equal to mass times gravity, so that's why we can make that substitution here, okay? And then area is A times G sub C, okay? So P, pressure, is equal to mg divided by A over G sub C, or P is equal to rho Vg, so rho for density, divided by A over G sub C, where m is the mass in pounds per mass, G is the acceleration due to the Earth's gravity, which is 32.17 feet per second squared. G sub C is 32.17 pound per mass foot per pound per force second squared. A is area in feet squared. B is the volume in cubic feet, and rho is the density of the fluid in pound per mass per cubic foot. So the volume is equal to the cross-sectional area times the height. And so that's why you're able to make this substitution, where P is equal to rho times AHG divided by A over G sub C. The A's cancel out. P is equal to rho HG over G sub C. So the pressure is equal to the density times the height times G divided by G sub C. Okay, and so the equation go back. Okay. So the equation tells us that the pressure exerted by a column of water is directly proportional to the height of the column and the density of the water, and is independent of the cross-sectional area of the column. The pressure 30 feet below the surface of a 1-inch diameter standpipe is the same as the pressure 30 feet below the surface of a large lake. So they give us an example problem. In a tank in figure 1 is filled with water that has a density of 62.4 pound per mass per cubic foot. And they ask that you calculate the pressures at depths of 10, 20, and 30 feet. So the equation that they use is P is equal to rho Hg divided by G sub C. So the pressure at 10 feet, they substituted 62.4 pound per mass per cubic foot times 10, and they divide 32.17 foot per second squared divided by 32.17 pound per mass foot per pound per force second squared, and they wind up with 624 pound per force per foot squared. And then they use this conversion factor, okay, to convert between feet squared and inches squared. Well, feet and inches, and they square that, okay. So what they wind up with is 4.33 pound per force per inch squared is the pressure at 10 feet, okay, at a depth of 10. Then they go into this problem as well, and they calculate the pressure at 20 feet. So everything remains the same except this value they place in the 20. And you wind up with a pressure of 8.67 pound per force per inches squared, okay? So the only thing they changed here was instead of putting the 10 here, they put in the 20. And then they're going to do the same thing at 30 feet, okay? So you see the only thing that changes is they put in the 30. And so they wind up with a pressure of, excuse me, 13 pound per force per inches squared. A cylindrical tank at 40 feet high and 20 feet in diameter is filled with water that has a density of 69.1 pound per mass per cubic foot. And they ask you what is the water pressure at the bottom of the tank? What is the average force for part B at the bottom? Okay. So in order to calculate pressure, pressure is equal to rho Hg over G sub C. P is equal to 61.9 pound per mass per cubic foot. H, they substitute in 40. And then of course, they multiply that by 32.17 foot per second squared divided by 32.17 pound per mass foot divided by pound per force second squared. Here they put in this conversion factor again. So the answer for part A is 17.2 pound per force per inches squared. Then for part B, they understand that pressure is force per unit area. They rearrange the equation to get force by itself. So the final equation that they use is force is equal to pressure times area. Okay, so they cross multiply. And area is equal to pi r squared. Okay, and so F is equal to 17.2 pound per force per inches squared times pi times r squared, which is 10 feet squared. And then, of course, they use a conversion factor to get this in inches, to get this H in inches. So that's 144 inches over feet squared. And so the force is equal to 7.78 times 10 to the 5th pounds per force. So Pascal's law, the pressure of liquids in each of the previously cited cases has been due to the weight of the liquid. Liquid pressures may also result from the application of external forces on the liquid. So consider the following examples. In figure 2 represents a container completely filled with a liquid. A, B, C, D, and E represent pistons of equal cross-sectional areas fitted into the walls of the vessel. And there may be forces acting on pistons C, D, and E due to pressures caused at different depths on the liquid. So assume the forces on the pistons is due to the pressure caused by the weight of the liquid are as follows. So A is equal to 0 pounds per force, B is equal to 0, C is equal to 10, D is equal to 30, and E is equal to 25 pounds per force. Now let an external force of 50 pounds per force be applied to the piston, and this external force will cause the pressure at all points in the container to increase by the same amount. So since the pistons all have the same cross-sectional area, the increase in pressure will result in forces on the pistons, all increasing by 50 pounds per force. So if the external force is 50 and is applied to piston A, the force exerted by the fluid on the other pistons will now be as follows. B will be 50, C will be 60, D will be 80, and E will be 75 pounds per force. And so the effect of the external force on a confined fluid, this was stated by Pascal. Pressure applied to a confined fluid is transmitted undiminished throughout the confining vessel of the system. Okay, so I will stop. So now we're going to talk about, after talking about Pascal's law, we're going to talk about control volume. So in thermodynamics, control volume is defined as a fixed region in space where one studies masses and energies crossing the boundaries of a particular region. And so this concept of control volume is very useful in analyzing fluid flow problems. The boundary of a control volume for a fluid flow is usually taken as the physical boundary or the part through which the flow is occurring. So the control volume concept is used in fluid dynamic applications, utilizing the continuity, momentum, and energy principles mentioned at the beginning of this chapter. And once the control volume and its boundary are established, the various forms of energy crossing the boundary with the fluid can be dealt with in the equation form to solve the fluid problem. So since fluid flow problems usually treat a fluid crossing boundaries of a control volume, the control volume approach is referred to as an open system analysis. So this is similar to concepts studied in thermodynamics. And there are special cases in the nuclear field where the fluid does not cross the control boundary. And in such cases, we study this as a closed system. So regardless of the nature of the flow, all flow situations are found to be subject to the established basic laws of nature that engineers have expressed in equation form. So conservation of mass and conservation of energy are always satisfied in fluid problems, along with Newton's laws of motion. In addition, each problem will have physical constraints, and this is referred to mathematically as boundary conditions. that must be satisfied before the solution to the problem will be consistent with the physical results. And of course, anytime you talk about boundaries, anytime you talk about limits, you're talking about what they do in calculus. Okay. And so volumetric flow rate, or V, of a system is a measure of volume of fluid passing a point in a system per unit time. The volumetric flow rate is calculated as the product of the cross-sectional area, A for flow, and the average flow velocity. So the equation is V is equal to A times lowercase v. So if the area is measured in square feet and the velocity is in feet per second, the results in volumetric flow rate measured in cubic feet per second. Okay. And other common units for volumetric flow rate are gallons per minute, cubic centimeters per second, liters per minute, or gallons per hour. And so the example problem that they give is that a pipe with an inner diameter of 4 inches contains water that flows at an average velocity of 14 feet per second. And they ask you to calculate the volumetric flow rate of water in the pipe. So they take equation 3.1 and they substitute for the area. For area, they substitute in pi r squared. So V is equal to pi r squared times lowercase v. They go in and substitute. Of course, you know, pi, that's 3.14. They put in the conversion factor. So they put in 2 and they divide it by 12 and they square that quantity times 14 feet per second. Okay, so they just did shorthand 1 inches. I'm sorry, 1 foot is 12 inches here. So they just shorthand and divide by 12 because they know that it's going to want to be division by 12, and they square all of that. So V is equal to 1.22 feet cubed per second. The mass flow rate of a system is the measure of the mass of fluid passing a point in the system per unit time. The mass flow rate is related to the volumetric flow rate, is shown in equation 3.2, where rho is the density of the fluid. So M is equal to rho times V. If the volumetric flow rate is in cubic feet per second, then the density is in pound mass per cubic foot. And equation 3.2 results in a mass flow rate measured in pound mass per second. So other common units of measurement for mass flow rate is kilograms per second, pound, and pound mass per hour. So make sure you get those, because make sure you get those equations. So I would highlight the different units that you can see this in. I would highlight this, and I would highlight the way that they talk about units here in this paragraph form. So I would highlight this one, okay? I would highlight that. So replacing V in equation 3.2 is appropriate terms for equation 3.1, and it allows direct calculation of mass flow rate, where mass is equal to rho times A times V. And so the example, that problem that they give is that the water in the pipe of a previous example had a density of 62.44 pound per mass per cubic foot. And they ask you to calculate the mass flow rate. So M is equal to rho times V. M is equal to 62.44 pound per mass per cubic foot times 1.22 cubic foot per second. And so the mass flow rate is 76.2 pound per mass per second. So in thermodynamics, you learn that energy is neither created nor destroyed. It's only changed in form, and the same is true for mass. And so therefore we have the conservation of mass, which is a principle of engineering that states that all mass flow rates in into a controlled volume are equal to all mass flow rates out of a controlled volume, plus the rate of change of mass within the controlled volume. So the principle is written mathematically where you have Mn is equal to M out plus delta M over delta T, where delta M over delta T is the increase or decrease of the mass within the controlled volume over a specified time period. Sorry, read that. Steady state flow, it refers to the condition where the fluid properties at any single point in the system do not change over time. These fluid properties include temperature, pressure, and velocity. And one of the most significant properties that is constant in a steady state flow system is the system's mass flow rate. And this means that there is no accumulation of mass within any component of the system. The continuity equation is simply a mathematical expression of the principle of conservation of mass. So for a control volume that has a single inlet and a single outlet, the principle of conservation of mass that for steady state flow, the mass flow rate into the volume must be equal to the mass flow rate out. So the continuity equation for this situation is M inlet is equal to M outlet. You can substitute for the M's. So you can substitute in rho AV inlet is equal to rho AV outlet. And for a control volume with multiple inlets and outlets, the principle of conservation of mass requires the sum of the mass flow rates into the control volume equal to the sum of the mass flow rates out of the control volume. So the continuity equation is more general, and it's expressed as sigma M inlet is equal to sigma M outlets. And so the Greek letter there, every time you see it, it just means add everything. Okay, it means sum total, it means add everything. So one of the simplest applications of the continuity equation is determining the change in fluid velocity due to the expansion or contraction in the diameter of a pipe. So steady state flow exists in a pipe that undergoes gradual expansion from a diameter of 6 inches to 8 inches. The density of the fluid in the pipe is constant at 60.8 pound per mass per cubic foot. If the flow velocity is 22.4 feet per second in the 6-inch section, what is the flow velocity in the 8-inch section? So in order to solve this problem, you need to use the continuity equation. And so you know that the mass flow rate in the 6-inch section must be equal to the mass flow rate in the 8-inch section. So letting the subscript 1 represent the 6-inch section and 2 represent the 8-inch section, you wind up with the following derivation. So M1 is equal to M2, or is PAV1 is equal to PAV2, where the V2 is equal to V1 times rho 1 over rho 2 times A1 over A2. And then they're able to substitute in for the A's. So, the cross-sectional area. So V2 is equal to V1 times pi r1 squared divided by pi r2 squared. Okay, and so now you can substitute in for that volume, which is 22.4 feet per second, times 3 inches squared over 4 inches squared. So V2 is 12.6 feet per second. So by using a continuity equation, you find that the increase in pipe diameter from 6 to 8 inches caused a decrease in the flow velocity from 22 to 12.6 feet per second. So the continuity equation So the continuity equation can also be used to show that a decrease in pipe diameter will cause an increase in flow velocity. So another example is the inlet diameter of a reactor coolant pump, shown in figure 3, is 28 inches, while the outlet flow is through the pump is 9,200 pound per mass per second. The density of the water is 49 pound per mass per cubic foot. And they ask, what's the velocity of the inlet point? So A inlet equals pi r squared. And they substitute in 3.14 times 14. And then they use the conversion factor. There's 12 inches in a foot. So 1 foot over 12 inches, and they square that whole quantity. And the A inlet is equal to 4.28 feet per second. M inlet is equal to M outlet. That's equal to 9,200 pound per mass per second. And so they're able to substitute for M, the rho AV inlet is equal to 9,200 pound per second. B inlet is equal to 9,200 pound per mass per second divided by A rho. And here they substitute in, so you wind up with B inlet is equal to 9,200 divided by 4.28 feet squared, divided by 49 pound per mass per cubic foot, with a V inlet being 43.9 feet per second. So the above example indicates that flow rate into the system is the same as that out of the system, and the same concept is true even though more than one flow path may enter or leave the system at the same time. Mass balance is simply adjusted to the state that the sum of all flows enter the system is equal to the sum of all flows leaving the system if steady state conditions exist. So an example of this physical case is included in this following example. So a piping system has a Y configuration for separating the flow as shown in figure 4. The diameter of the inlet leg is 12 inches. The diameters of the outlet legs are 8 and 10 inches. The velocity in the 10-inch leg is 10 feet per second. The flow through the main portion is 500 pound per mass per second. The density is 62.4 pound per mass per cubic feet. And they're asking what is the velocity out of the 8-inch pipe section. Okay. So in order to solve this problem, you use A, and the subscript 8 for the 8-inch section is equal to pi times 4 inches, and that's times the conversion factor, 1 foot over 12 inches, and they square the quantity. So A in the 8-inch section is 0.349 feet squared. A in the 10-inch section is pi times 5, divided by 12, and that quantity is squared. So A in the 10 inch section is 0.545 feet squared. And so sigma m inlets is equal to sigma m outlets. So m 2 is equal to m10 plus m8. M8 is equal to M12 minus M10, and they substitute in for the M. So rho AB is equal to M12 minus P AV for the 10-inch section. And so V8 is equal to M12 minus rho AV for the 10-inch section, divided by rho A for the 8-inch section. So they substitute in after they've got this as your final equation that you'll use. Okay, so everything else is derivations. Okay, if you use any of those other equations, you're going to get confused. This is the one that they use. So 500 pound per second minus 62.4 pound per mass per cubic foot times 0.545 feet squared times 10 divided by 62.4 pound per mass per cubic foot times 0.349, and you get a velocity in the 8-inch section of 7.3 feet per second squared. So take your time and do the summary section. So let me pause it here. So take your time to do the summary section. So now we're going to talk about Bernoulli's equation. Bernoulli's equation is a special case of the general energy equation that is probably the most widely used tool for solving fluid flow problems. It provides an easy way to relate to the elevation head, the velocity head, and the pressure head of a fluid. And it's possible to modify Bernoulli's equation in a manner that accounts for head losses and pump work. So in this chapter, we're going to describe the relationship between Bernoulli's equation and the first law of thermodynamics. We're going to define the term head with respect to its use in fluid flow, explain the energy conversions that take place in a fluid system between the velocity, elevation, and pressure heads as flow continues through a piping system. And then given the initial and final conditions for this system, we're going to calculate the unknown fluid properties using the simplified Bernoulli equation. Then we're going to describe the restrictions applied to Bernoulli's equation when presented in its simplest form. And we're going to explain how to extend Bernoulli's equation to more general applications and relate Bernoulli's principle to the operation of a venturi. So the conservation of energy principle states that energy can't be created nor destroyed. And this is equivalent to the first law of thermodynamics, which is used to develop the general equation in the module for thermodynamics. So equation 3A is a statement of the general energy equation for an open system, where Q is equal to U plus PE plus KE plus PVN is equal to W plus U plus PE plus KE plus PV out, and plus U plus PE plus KE plus PV stored. Okay, so you know that PE is potential energy, KE is kinetic energy, and PV is another way of talking about work, because you can make the substitution for work and you can say that it's P times U. So Q is equal to heat in BTU. U is internal energy in BTU. PE is potential energy in foot pound per force. KE is kinetic energy in foot pound per force. P is pressure in pound per force per foot squared. V is volume, which is in cubic feet, and work is foot-pound per force. So the simplified Bernoulli equation, this results from the application of the general energy equation, which was aforementioned, and the first law of thermodynamics to steady state flow in which work is done on or by a fluid. No heat is transferred to or from the fluid, and no change occurs in the internal energy, i.e. no temperature change of the fluid. So under these conditions, the general energy equation is simplified to equation 3.9, where PE plus KE plus PV1 is equal to PE plus KE plus PV2. Substituting in the appropriate expressions for potential and kinetic energy can help us rewrite this equation. So mgz 1 over gc, so that's for potential energy, plus mv1 squared over 2gc, that's for kinetic energy, plus p1 v1 is equal to mgz2 over gc, plus mv2 squared over 2gc, plus p2 v2. So m is equal to the mass, which is in pound per mass. Z is the height above the reference in feet. V is the average velocity in foot per second. G is the acceleration due to gravity, and that's 32.17 foot per second squared. And GC is the gravitational constant, which is 32.17 foot pound per mass per pound per 4 seconds squared. So note that the factor GC is only required when the English system of measurement is used and mass is measured in pound mass. It's essentially a conversion factor needed to allow the units to come out directly. So no factor is necessary if the mass is measured in slugs or if the metric system of measurement is used. Each term in the equation 310 represents a form of energy possessed by a moving fluid, potential energy, kinetic energy, and pressure-related energies, so such as work. So in essence, the equation physically represents a balance of kinetic energy, potential energy, and P times V, which is another way of talking about work. Okay, so that if one form of energy increases, one or more of the others will decrease in order to compensate, and vice versa. So multiplying all the terms in equation 310 by a factor of GC divided by M over G results in the form of Bernoulli's equation shown here, which is Z1 plus V1 squared over 2G plus P1 V1 GC over G is equal to Z2 plus V2 squared over 2G plus P2 V2 GC over G. So since the units for all the different forms of energy in equation 311 are measured in units of distance, these terms are sometimes referred to as heads, like the pressure head, the velocity head, and the elevation head. And the term head is used by engineers as in reference to pressure. It is a reference to the height, typically in feet, of a column of water that a given pressure will support. And each of the energies possessed by a fluid can be expressed in terms of head. The elevation head represents the potential energy of a fluid due to its elevation above the reference level, and the velocity head represents the kinetic energy of the fluid. And the height in feet that a flowing fluid would rise in a column if all of its kinetic energy was converted to potential energy. And the pressure head represents the flow energy of a column of fluid whose height is equivalent to the pressure of the fluid. So the sum of the elevation head, the velocity head, the pressure head of a fluid is called the total head. And Bernoulli's equation states that the total head of a fluid is constant. So Bernoulli's equation makes it easy to examine how energy transfer takes place among elevation head, velocity head, and pressure head. And it's possible to examine these individual components of piping systems and determine what fluid properties are varying and how much energy balance is affected. So if a pipe containing an ideal fluid undergoes general expansion in the diameter, the continuity equation tells us that the diameter and flow get bigger. The flow velocity, it must decrease to maintain the same mass flow rate. So since the outlet velocity is less than the inlet velocity, the velocity head of the flow must decrease from the inlet to the outlet. So if a pipe lies horizontal, there is no change in the elevation head. Therefore, the decrease in velocity head must be compensated for by an increase in the pressure head. So since we're considering this ideal fluid is incompressible, the specific volume of the fluid doesn't change. The only way that the pressure head for an incompressible fluid can increase is for the pressure itself to increase. So Bernoulli's equation indicates that a decrease in flow velocity in a horizontal pipe will result in an increase in pressure. And the constant, so if a constant diameter pipe containing an ideal fluid undergoes a decrease in elevation, the same net effect results, but for different reasons. And in this case, the flow velocity and the velocity of the head must be constant to satisfy the mass continuity equation. So the decrease in elevation head can only be compensated for by an increase in the pressure head. Again, the fluid is incompressible, so the increase in the pressure head must result in an increase in pressure. And although Bernoulli equation has several restrictions placed on it, there are many physical fluid problems in which it is applied. As in the case of conservation of mass, the Bernoulli equation is applied to problems which there is more than one flow that may enter or leave a system at the same time. Of particular note is the fact that series and parallel pipe problems are solved using Bernoulli's equation. So the example that they give is assume frictionless flow along a long horizontal canonical pipe. The diameter is 2 feet at one end and 4 feet at the other. The pressure head at the smaller end is 16 feet of water. And if the water flows through this cone at a rate of 125.6 cubic feet per second, find the velocity at the two ends and the pressure head at the larger end. So the solution is to use V is equal to A times V1 is equal to A1 times lowercase v1. V1 is equal to, so they get V1 by itself. V1 is equal to capital V1 over A1. And then V2 is equal to capital V2 over A2. And so they plug in and solve because we're trying to find the velocities at these two ends. So the velocity at the first end is 125.6 cubic feet per second divided by pi, which is 3.14 times 1 foot squared. And that velocity is 40 feet per second. The velocity at the second end is 125.6 cubic feet per second. And that's divided by pi times 2 squared. And so V2 is 10 feet per second. Then Z plus V1 squared over 2G plus P1 V1 times GC over G is equal to Z2 plus V2 squared over 2G plus P2 V2 times GC divided by G. And so what they do with this equation is that they try to get P2 V2 times GC over G by itself, and that is equal to P1 V1 GC times GC over G plus Z1 minus Z2 plus V1 squared minus V2 squared divided by 2G. And then they plug in and solve. So this is the equation that they use. 16 feet plus 0 plus 40 squared minus 10 squared divided by 2 times that constant, which is 32.17 foot pound per mass divided by pound per force second squared. And so once they plug in and solve, they get 39.3 feet. They get 39.3 feet. So we do have restrictions on the simplified Bernoulli equation. Practical applications of this simplified Bernoulli equation to real piping systems isn't possible due to two restrictions. One serious restriction of the Bernoulli equation is in its present form is that no fluid friction is allowed in solving these piping problems. Therefore, equation 310 only applies to ideal fluids. However, in reality, the total head possessed by the fluid cannot be transferred completely from one point to another because of friction. So taking these losses of head into account would provide a much more accurate description of what takes place physically. So this is especially true because one purpose of a pump in a fluid system is to overcome the losses in pressure due to pipe friction. The second restriction on Bernoulli's equation is that no work is allowed to be done on or by the fluid. And this restriction prevents 2 points in a fluid stream from being analyzed if a pump exists between these 2 points. So since most flow systems include pumps, this is a significant limitation. Fortunately, the simplified Bernoulli equation can be modified in a manner that satisfactorily deals with both head losses and pump work. So the extended Bernoulli equation can be modified to take into account gains and losses of head. The resulting equation, referred to as the extended Bernoulli equation, is very useful in solving most fluid flow problems. In fact, the extended Bernoulli equation is probably used more than any other fluid flow equation. And the extended equation is Z1 plus V1 squared over 2G plus P1 V1 GC over times GC over G plus HP is equal to Z2 plus V2 squared over 2G plus P2 V2 times GC over G plus H to the F, where Z is the height above the reference level, and that's in feet. V is the average velocity of the fluid, that's in feet per second. P is equal to the pressure of the fluid, that's in pound per force per foot squared. V is the specific volume of the fluid, and that's in cubic feet per pound per mass. H to P is the head added by the pump, and that's in feet. HF is the head loss due to fluid friction, and that's in feet. And G is the acceleration due to gravity, and that's in feet per second squared. So the head loss due to the fluid friction, HF, represents the energy used in overcoming friction caused by the walls of the pipe. And although it represents the loss of energy from the standpoint of fluid flow, it does not normally represent a significant loss of the total energy of the fluid. It also does not violate the law of conservation of energy, since the head loss due to friction results in an equivalent increase in the internal energy U of the fluid. These losses are greatest as the fluid flows through entrances, exits, pumps, valves, fittings, and any other piping with a rough inner surface. So most techniques for evaluating head loss due to friction are empirical. They're based exclusively on the experimental evidence, and they're based on a proportionally constant called the friction factor, F, which will be discussed in the following section. So a problem that uses the extended Bernoulli equation, you have water that is pumped from a large reservoir to a point of 65 feet higher in the reservoir. How many feet of head must be added by the pump if 8,000 pound per mass per hour flows through a 6-inch pipe and the frictional head loss is 2 feet? The density of the fluid is 62.4 pounds per mass per cubic foot, and the cross-sectional area of the 6-inch pipe is 0.2006 feet squared. So to use that Bernoulli equation, you use M2 is equal to PA2 V2, and you get V2 by itself so you get V2 by itself, and that's equal to M2. Okay. So the equation is M2 is equal to rho A2 V2. You get V2 by itself. So V2 is equal to M2 over rho A2. And you plug in and solve. So this is the equation that you want to use. V2 is equal to 8,000 pound per mass per hour divided by 62.4 pound per mass per cubic foot times 0.2006 feet squared. So V2 is equal to 639 foot per hour. And they go from hours to seconds. Using a conversion factor, 1 hour is 3,600 seconds. So 639 foot per hour divided by 3,600 gives you a V2 of 0.178 feet per second.